The pressure drop per unit length, or dP over L, is an important factor in designing flows in pipe systems or for understanding flows in natural conduits. This equation here, the Darcy-Weisbach equation, is set up to give the pressure drop per unit length in circular pipes. And it says that that factor, or the pressure drop per unit length, is equal to these terms: the density, velocity squared, the diameter of the pipe, and this friction factor that depends on the Reynolds number. The friction factor characterizes the friction losses within the flow. So the friction factor is shown here. Friction factor is a function of Reynolds number plotted on the Moody diagram. And what's happening here is at low Reynolds numbers, here below about 2000, the friction factor is equal to this line, which is 64 over the Reynolds number. And then you go through a transition region here, and this region here describes flow in the turbulent regime. And all these lines are the friction factors for pipes of where the wall roughness varies. So the wall roughness is given here. It's hard to read, but this is right there is the roughness, the kind of amplitude of the roughness on the wall divided by the diameter of the pipe. So you get these different curves for different roughnesses because as the pipe gets rougher, you have more friction on the wall and more loss as a result of that. So what I want to do is use this analysis of friction as a function of Reynolds number to verify the analysis of flow in a circular tube. And what we'll do is go through the analysis and we'll calculate the Reynolds number using this equation, and we'll calculate the friction factor using basically the Darcy-Weisbach equation where we've solved for the friction factor. One thing that I should point out is this term here, dP, this is the pressure drop, the difference in the pressure over this length. And so when we do the verification, we'll have to calculate that. So let's go over to Comsol. So here's the analysis. Let's just go from the top of the model builder and work our way through. So the model has several parameters shown here in global definitions. The average velocity will be important because we'll vary that to vary the Reynolds number. The radius and the length, these parameters are just used to set up the geometry. So they aren't really essential, but they're convenient. So expand out definitions. I've got two of them here, variables. And what I've got here under the variable definitions are some of the equations that we saw on the PowerPoint. Here's the equation for the Reynolds number, the equation for the pressure drop, the Moody friction factor. So this one here and this one here, these equations are right from the PowerPoint, and they'll be what we use to plot to create the Moody diagram. Now, one thing I should point out here, this equation for the pressure drop, it uses this term here called ab inflow parentheses P. So that is a function that I defined down here. And I created this by right-clicking on definitions, going to function, going to model coupling, and down here to average. So what that does is it integrates over a region that you specify and determines the average parameter that you give it. So what I did is set this up to integrate over the boundary. So I selected boundary, I gave it a name here, and I selected this boundary right here. We'll take a look at the geometry here in just a second. And now you can see that this is the name, and so up here in the definitions where I use that name and then put in parentheses P, what I will do is this function will calculate the average pressure along that boundary that I specify, and it will write that into this variable name. Okay, so geometry. This geometry consists of two rectangles. Well, first of all, it's a axis symmetric model. So here's the axis of symmetry, this red dashed dotted line. And so the geometry will be revolved around that line. And there are two rectangles, here and here. And they're just specified using these two rectangles here. You can see also that I've used the parameters, radius and length, that I defined up here so that I can control this geometry and change it just by changing the parameters if I like. And so what I'm going to do is use these two rectangles to create a tube, and we imagine then this is the radius from here to here. This tube gets formed by revolving these rectangles around the axis. And the reason I'm going to do that is because I'll have a flow coming in here at the bottom and leaving at the top. And then the flow, there will be some entrance effects. And so the flow will, the geometry, or the distribution of velocity will change with distance from the entrance point. And so I just want to give this this amount of distance from here to here for the velocity to stabilize. And then velocity and the pressure. And so then I'll calculate the average pressure here and take the difference between the average pressure there and there to calculate the pressure drop. Okay, so under materials, I'm selected water as the material, and when I set this model up, I used laminar flow physics, and so we have a variety of things, of settings in here, but actually when it's set up for laminar flow, we're just going to use all of the default settings. Make sure that the two subdomains here are selected, and then let's expand it out and take a look at some of the settings here. The fluid properties I have just inherited from the material, and the inlet condition for the laminar flow, I'm using the laminar inflow boundary condition with the average velocity here set to the variable name average velocity. And outlet, I'm just using pressure no viscous stress boundary condition. So the mesh in this case is just a default mesh, but it's default with physics controlled, and what is produced is quite a dense mesh here. Let's zoom in on it and take a look at the details. So you can see that it's a triangular mesh here in the body of the conduit, and it gets finer as we get closer to the wall. And let's zoom in a little bit more on the wall. And so what we see here is that the shape of the mesh elements changes as we get to the wall. And the mesh right here, right next to the wall, consists of about 5 or 6 rectangular elements. And those are put in by default because the code recognizes that it's using these fluid flow physics and that this is a wall, and there'll be a boundary layer created at the wall, and so it puts these elements in to more accurately represent the boundary layer. So under the study, what I'm doing here is just using a stationary study, so we're just going to be doing steady state, and I'm using a parametric sweep to calculate various velocities. And I set up 2 studies, one for laminar and one for turbulent conditions, and they're set up similarly, except the parametric sweep covers a different range of velocities. So I know from calculating the Reynolds number and experimenting around that this range of velocities will be within the laminar range of flow in this conduit. And then here under the turbulence study, I have another range of parameters that's in the turbulent range. Okay, so another thing let me point out is if you go here to stationary and look at the setup for the solver, we're selecting the laminar flow physics, but here under values of dependent variables, what I did was to check this, and the default is just to use the initial expression of zero solution. That's what you get for the default for values of dependent variables. But what I did was to change it. Let's try to expand this out here. And use the solution and the laminar flow solution. And the parameter value, average velocity, will be automatic. And so what this will do is calculate a solution using one parameter, and I set it up so the velocities go from low to high. And so it calculates the solution for one velocity and then uses that as the initial conditions for the next solution with a higher velocity. And so that is a way to basically give a better initial guess at the solution and improves convergence of the model with the next higher velocity. So I set that up for the turbulent solver as well. It's got this higher range of velocities and then this value of dependent variable. So what I did then was to set this up for laminar, run this study, and do the parameter sweep. And then to run the turbulent, I went in here to the physics interface, and I go down here to the turbulent model type. So when it's set up for laminar conditions, then we're not using a turbulence model. But when it's in the turbulent range, then we use this RANS, the Reynolds average Navier-Stokes equation. And here are the equations that are solved. And there are a couple of different turbulence models that are available. Here are the possibilities. And I just used K epsilon, which is the default. So what happens when you make that change is the name changes here. And so I made that change in the setup, and then I ran the turbulent study. And then I got results for laminar conditions and results for turbulent conditions that I can view at the same time in the results. So if we go down here, the data sets, I've got data sets for laminar and turbulent conditions. And here's really what I'm after. I want to take the results and compare it to the Moody diagram. So I've got a plot here that is called Moody diagram, and I'm plotting three different things. So laminar range, this is plotting the function that I created that we saw up here, up in the definitions, called Moody F, and that's calculating the Moody friction factor. And I'm plotting it as a function of this x-axis expression, which is the Reynolds number. So right here, we don't really see it labeled, but this is friction factor as a function of Reynolds number. And we can label that, actually. Let's just call that RE, and let's call this Moody F. That should be a little clearer. And so let's see. This is the numerical results here shown in. Let me see. Let's make it sure it's clear. Let's specify this blue plot. And the blue plot, it's actually right here. Maybe it'll be a little bit clearer if I made it dashed. Yeah. So there it is. Those are the numerical results. And then the analytical solution for the friction factor in the laminar range is easy. It's just 64 divided by the Reynolds number. So I plot that as a function of the Reynolds number, and that's the red line there. And so you can see that the numerical and analytical results are quite close. And then the results for the turbulent analysis are shown here with this plot, and it's shown here with this blue line. You can see it getting thicker there. And what I'm doing is plotting Moody F, this Moody F function, the function of Reynolds number, but I'm using the turbulent data set here, as opposed to up here on this plot. I'm basically plotting the same thing, Moody F as a function of Reynolds number, but I'm using the laminar data set. I also determined the velocity profile here with this plot, and this is for the laminar case. You can see somewhat of a parabolic velocity distribution. This is just showing from the center of the pipe out to the wall. And we also have these 3D plots where we're looking at the velocity distribution here under laminar conditions. And same thing, but under turbulent conditions here. And you can see that under turbulent conditions, we've got this core in the center of the tube where the velocity is really fairly uniform. And that's quite different from the laminar condition where the velocity is continuously changing. And that's one of the consequences of turbulent flow. Okay, so really when it comes right down to it, what we want to do is take these data for the Moody diagram and plot them on the actual Moody diagram to check and see how well we're doing. So what I did to do that was to go here to the data. This is the plot that has the data that are shown here. And I want to show this on the Moody diagram. So I would go and right click and go add plot data to export. So I do that. It goes down here to export. It gives me this plot 1, it's called. Here's a plot of those data. And so what I do now is to go here to browse, and you can see I've got a variety of text files here, so I can reuse one of these, or let's go, and this is laminar, so let me call this lam2. Hit save. And now, once you've got it set up, that tells you what file to write it to, but you have to go here to export to write that file. Now we take the data. What we've just done is taken the data that's calculated by the model and shown here in this plot and written it to a data file that we can then open in Excel. So now if I go to Excel and take a look here at the, just go to open the file, and here's the laminar 2 file that we just created. So we open it and use delimited, and I would use space delimited and hit OK, and it comes in like this. So here's some description of the analysis, and these are the data that we're after. Okay, so what I did was to run the model and import the data and create a file that is shown here. And we pretty much got the data in just like I said there, but I also copied and pasted the Moody diagram. And so this is shown here. This is just a picture. And what I did was to put the picture in there, and then if I click here, this is a plot that is made in Excel. And so I think you can see right here, these numbers are small, but these are this is the y-axis, and the x-axis values are here, 100, 1000, and so on. Okay, so what I did was to make this plot and make the background transparent, and it's just overlaying on this picture of the Moody diagram. So I'll move it here. So let's see. If I move this whole thing, there. So I just pick it and I can move it around. But what I did then was to move it and get it adjusted. See there, this is 0.01, there's 0.01 underneath it on the Moody diagram. There's 0.1 on the plot and 0.1 on the Moody diagram. So I just adjusted it to get it lined up. And then I also got these values lined up. So it has to move over a little bit more. And let's see. So it takes a little bit of fiddling, but yeah, that's getting pretty close. There's lining up along X and lining up along Y. It's off a little bit here. But it takes a little bit of fiddling, but you can get them lined up really quite well, these axes lined up, and that way you can take data, plot it accurately using Excel, and then compare it to this Moody diagram. And as far as I know, the data for the Moody diagram are hard to come by. It's easy to find this plot of the diagram as a picture. And so the easiest way to compare seemed to be to overlay the Excel plot onto this actual image.